textbook they say it's easy to show that this is true. And that's a lie. It's not easy to show. They always do that. And then from here, we want to make some approximations to make this much more useful because we have a very exotic term for A over F, which includes two different exponential terms and two coefficients out in front. And more importantly than getting the exact answer, because this barrier is not real, there is no experiment that relates exactly to this barrier. So more than getting the precise answer, we're interested just in the behavior of this thing. So what they do is they say, let us assume that the barrier is high and wide. And let me explain that. When you assume that the barrier is high, then you're assuming that V is significantly larger than E. So let's start by just saying V larger than E, perhaps twice E, something like that. So that the height of the barrier, what we're looking at is the height of the barrier, is significant. E might be here, V might be there, something like that. In other words, that it's not obvious that this thing would go over as well below. Well, in that situation, then I would claim that here, looking right here, or here, K2 over K1 minus the other way around, K1 over K2 is approximately equal to K2 over K1. Why? Because as you recall, K2, which is 2me minus v over h bar, this part is under the square root, divided by 2me over h bar. When you make this number significantly larger than that number, then the number down below is relatively trivial. So if you turn it over, you end up with this term here being relatively unimportant compared to this term. So what we end up with is K2 over K1, roughly speaking. Also, let us assume that the barrier is wide, and that is that L is fairly large. Meaning, as you recall, there is an exponential decay through L, and there's enough room through L for the decay to be significant. In other words, that the amplitude on the one side is significantly larger than the amplitude on the 3 side, because L is wide enough that the exponential decay is significant. If so, then e to the K2L, K2L is significantly larger than e to the minus K2L. So that basically, that part of the exponential is significantly larger because K2 suffers in that barrier. So L is fairly large. E to something to the L power is a lot bigger than e to 1 over e to that same power. Hence, therefore, we can ignore that. So using these approximations, it's easy to show, and I'm just going to use that term now without going through all the math, that A over F is approximately equal to 1/2 plus I K2 over 4 K1 e to the I K1 plus K2L. Using those two approximations, so if you simply say that, that the barrier is both high and wide, you're saying that there's a significant difference between V and the E, and L is large enough that there is a significant decay of the amplitude of the wave function through L. Then you can dramatically decrease the complexity here with tricks like this, and we come up with this approximation. High and wide, we can use that approximation. So of course the conjugate of this thing, A over F star is then going to equal, just replacing the I with a negative I, 1/2 minus I K2 over 4, 1, e to the I K1 plus K2, e to the minus I K1 K2 L, like that. So I have 1/2 minus I K2 over 4K1 e to the minus I K1 plus K2 L. Great. Why is that great? Because now we're ready to write down T, which was defined as F star over A star. So multiply these two together, flip them over, and what do you get? You get 16 over 4 plus K2 over K1 squared, and this entire thing is e to the minus 2 K2F.
What was T?
Say again?
What was T supposed to be?
What is T? Good. T is the transmission probability. That's where we were trying to figure out how likely is it that the particles actually get through the barrier. So that's what T was, the transmission probability. And it comes out to be approximately this with our approximations. And let's take a quick look at K2 over K1, which you see right here. So K2 over K1, did I square it? Yes, I did. I squared the thing. Is then going to equal 2m, where's KT? E minus, V minus E, I gotta write that backwards over there too. Remember K2 was the other way around. I think I wrote it backwards here. Make sure you change this because we were talking K2 here, not K prime. So in this case it was V minus E. My apologies for writing that backwards on the board. V minus E over H bar squared divided by 2ME over H bar squared. Which of course, as you can see, immediately the H bars go away. H bar squared goes with H bar squared. 2M goes with 2M. And we end up with, well, let's write it down here instead of over there. What do we have? We have it's V minus, V over E minus 1 is what we have for this one. And of course, that means, ladies and gentlemen, if you look at this term right here squared, put it right in here, 16 over 4 plus that, whatever that is, it turns out that this creature right here is never far away from 1. I'm going to put 1 question mark. It's about a 1. That's all it is. Now you can see the simplicity. Once we've done all of this approximating, of course, now we have T is equal to E to the minus 2 K2F. Wow. We started with this, and we ended with that. Yes, provided our two assumptions are fulfilled. What were the two assumptions? Assume the barrier is what? Wide and high, yes. So if you are asked the transmission probability in a problem like this, and you have a step function, you ask yourself, is the barrier both high and wide? Meaning, is V significantly above E, maybe twice as high, something like that? And is L large compared to the dimensions of the objects involved? Then you can say, I'm given this problem, since the barrier is high and wide, I will use this approximation to determine the transmission probability of the particle through the barrier. And if for some reason you are certain that you do not have high or wide, then your argument is, you say, I have for certain that it is not high or it is not wide, therefore my approximation will not work, I cannot answer this problem. Okay? So if it's high and wide, you use this, everything's great. If it's not high and wide, verify by some statement, by some argument, verify that it's not one or the other. At that point, you are free to not answer the problem. The correct answer is, I cannot answer this problem. Go ahead.
Is the k in the exponent supposed to be k2? Or
K2, did I write K1?
You just said k.
I wrote K nothing.
Okay.
Okay, just checking.
I wrote K nothing, it's K2, yes. K2, where are K2? Up. Yeah. And of course you knew this was coming, didn't you? There is a problem. It's not a quiz. It's an in-class problem. Make sure everybody has a copy of it. I'll read it with you. If you could turn that in, yes.
Velocity is the rate of energy. L space. Potential energy.
Yeah.
In space. Oh, that's what I
Electrons with energies of 1 eV and 2 eV are incident on a barrier 5 eV high and 0.5 nanometers wide. Find their respective transmission probabilities. How are these affected if the barrier is doubled in width? So there's 4 answers. Electrons at 1, 2 eV, half a nanometer wide, or 1 full nanometer wide for the barrier.
Professor, what would you consider wide?
Is the barrier wider than the electron?
Okay.
L now becomes twice as big, so you put in a 2. And what I get for T prime 1 is 2.1 times 10 to the minus 9 as my transmission probability. And if I put in 2 eV electrons with this double wide barrier, I get about 1.9 times 10 to the minus 8. This, by the way, says, look, this is about 5 times 10 to the what? Minus 5, less likely. And this is about 1 times 10 to the minus 4, less likely to happen. So, and I would like this, if this was a final exam problem, you got the 4 answers, and the nice thing is then to talk about them. In other words, what we've just noticed is that if the difference in energy of the particle, if it differs by a factor of 2, then the transmission probability changes by a factor of about 3. But if the width of the barrier changes by a factor of 2, you can see that it is significantly less likely. You double the width of the barrier and your transmission probability drops down dramatically. Dramatically. In other words, these kinds of particles striking these kinds of barriers are much, much more strongly affected by the width of the barrier than they are by the height of the barrier. That would be your final conclusion. You would say, here are my 4 answers. That's not good enough. then you say, clearly the particle is far more affected by the width of the barrier than it is by the height of the barrier, clearly. So when you're doing experiments like this, the width of the barrier is going to make huge differences in your experimental results. The height of the barrier is going to make only subtle differences in the results of your experiment. So there's two things that you're probably not used to, and that is, remember, always tell me exactly why you're going to use an approximation. Before you do anything else, you start out with this. Then you go ahead and do the routine work, just do the calculations. And when you're done, look at the results and tell me what these results imply. And you're not Physics 1 students, but what the Physics 1 students would say, well, what these results imply is that 1 in 22,000 get through here, 1 in about 7,000 get through here. They would just tell me what the answers are. You compare the answers and say, double the height of the energy, it doesn't change the results very much. Double the width of the barrier dramatically changes the results. Therefore, tunneling problems depend far more on width of barrier than height of barrier. All right. What fun, huh? That was an insincere chuckle when I said what fun.
Chuckle, chuckle.
I'll pick those up in a few minutes, or maybe you can just drop them off there on the way out the door. Next thing I'd like to do is to simply imply to you one more solution, and that is the solution to the harmonic oscillator. Do you recall what is a harmonic oscillator? When you use that term, it's a very specific system. That's a result, yes. It will take a sinusoidal oscillation, but it's any system under the influence of whose law? That's right, Hooke's law. So, a harmonic oscillator, Hooke's law. What does Hooke's law look like, you remember? Minus K X equals what? F equals minus Kx. So please remind me, physically speaking, what does this mean? The force is what? It's proportional to the displacement. The further you displace something, the more the force is. And it's a linear relationship. You double the distance, you get twice the force. And the negative sign means what?
It's in the opposite direction.
Yeah, okay, yes, or a restoring force. So, Hooke's law is a restoring force. The force is proportional to the displacement. And you might have done an experiment. A low amplitude pendulum is Hooke's law. A spring system, a mass, an oscillating mass on a spring is a Hooke's law system. You may have done an experiment like that way back in Physics 4. I know that's in the distant memory. So, let's write down Newton's second law, F equals ma. But of course, for us, M, since I'm writing it without much qualification, you can be suspicious that we're probably talking about classical mass. Things are moving relatively slow. And then MA is, of course, d squared x. d squared, we're going to put x dt squared. It's the second time derivative of the position. Yes, we used x for the position back in those days, equals minus kx, like this. So, let's talk a little bit about the potential energy. The potential energy, of course, remember the mass on the spring. I don't know, did you guys do that one where you either displaced it vertically or you put it on a linear air track and displaced it horizontally? The work, of course, is the force times the distance the force moves. But in this case, we want to move this thing from potential energy, move from x equals 0 to x equals x. That looks like a silly statement, but of course what we're talking about is just some arbitrary position. And we'll be specific in a few moments. Now there's an implication, I've just implied something here, and that is, what is the position x equals 0? You don't say the 0 position on the x-axis. Oh, no.
Starting.
Say again? That's the position where no force acts, or the rest position if the system is in equilibrium. If it has stopped, it's in equilibrium. That's the position from which everything is measured. If you're imagining the mass on the spring, that's where you lower it down, and then wherever it comes to rest, and you move your hand away like that, wherever it comes to rest, that's what you call x equals 0. That's the position you call x equals 0. So that's where there's no net force. Wherever that is, that's where we define it as x equals 0. And so, so one good solution to this thing, and let's see, how did I rewrite this? I just moved that over there. One good solution to this thing is just to write that d squared x dt squared, so I'm obviously moving that, is equal to, plus, let's move it, d squared x dt squared. So we move that over there, divide by m, and we get plus k over m x equals 0. A solution to this differential equation would be, and you might, when you get a chance, just show that this works. You don't have to do it right now. A cosine of 2 pi nu t plus phi. 2 pi nu t plus phi. Where phi is an initial displacement, I just put it there for initial displacement. And nu, as you recall, is the frequency, so it's 1 over 2 pi times k over m under the square root. So this is a solution that would work for us. Now, for the harmonic oscillator, Schrodinger's equation for the harmonic oscillator would be, of course, d squared psi dt squared, and then of course it's plus 2m over h bar. Now it's e minus v, e minus 1/2 kx squared psi equals 0. So obviously I look at the lowercase size, and this is a steady state situation. Wait a minute, where did this come from? Right here, 1/2 kx squared. I thought it was kx.
Kinetic energy of oscillating.
That's right, you have to do the work. You have to calculate the work. And in fact, you don't have to really do the integral, do you? Because you know that the force and the distance, and now all I'm doing is measuring how far from the equilibrium position, then the force and the distance is this, and the work, in a plot like this, the work is what? It's the area under the curve. So this is a triangle, which is part of a rectangle, so of course the work here, work equals area, which is 1/2 k x squared. F is kx times x, 1/2 kx squared. So you don't even really have to do it with a nice simple thing like that. Draw a quick little picture and say, aha, the work moving this thing from x equals 0 to x equals x is just going to be 1/2 kx squared. The work is the area under that plot. Hence, therefore, this is the potential energy term. This is the kinetic energy term, just like we have to have in Schrodinger's regular equation. So we're really ready to go, aren't we? And for some reason, I actually did the calculation. So we're ready to go, aren't we? No, we're not. We're ready to just state the answer. So what psi works? Here's Schrodinger's equation. Notice this time now we have a potential which is spatially dependent. Unlike the step function where we either have a constant v or no v at all, here we have a v, a potential function that is dependent on x. That's why we're not treating the math on how to solve this thing. I'm just going to tell you what the solution is. We're not going to go through the solution because it takes a lot lot of labor to get that function involved right in this part and find a solution to it. Here's the answer. Notice I put psi sub n because just like you would expect, we're going to end up with answers that are n dependent. They are only certain allowed discrete values. The answer is 2m nu over h bar, 2m nu over h bar raised to the 1/4 power times 2 to the n times n factorial raised to the -1/2 power times the Hermite polynomial n in terms of y, which then is multiplied times minus y squared over 2. And y is this factor right here. So this is a Hermite polynomial. Are you familiar with the Hermitian?
No.
Hermite? Okay. I'll find Hermite polynomials for you somewhere and list them for you. There's a lot of math. You might imagine there's a lot of math to get from here to here. And I don't want to do the math, and I don't want to hold you responsible for the math. But what I wanted to say was simply, this is the traditional way of doing things. First, we put a particle in a box and solve Schrodinger's equation. Okay, that shows us how Schrodinger's equation is used. Now, as a challenge, you put the particle behind a step function, behind a barrier, and you solve that. And you come up with an interesting solution which has to be approximated. It almost can't be solved in its exact form, and then have an experiment that agrees beautifully with it. So we approximate that. Then you come along and the next problem you solve is put the particle in a Hooke's law situation, a harmonic oscillator. And again, you come up with an ensemble of answers. You come up with an eigenfunction for your wave function. Somewhat more complicated now. And then finally, the last problem is, guess what? Put the electron in orbit in a hydrogen atom. So now the electron is under the influence of a slightly more complicated force. Not such a simple force, but a slightly more complicated force. So, if we're going to skip the math on this, we're going to skip the math on that one as well. Finally, when you're all done, we know that the Bohr model of the hydrogen atom matched the solutions that we got experimentally perfectly. Therefore, if Schrodinger is going to be correct, he should come up with the same answers. He does. In complete detail. Finally, for the first time, Schrodinger's equation gives us the solutions to the hydrogen atom in complete detail. Even explaining a few things that we didn't know to begin with. So, typically there are 4 problems for which you use Schrodinger's equation to begin with. Particle in a box, particle behind a barrier, harmonic oscillator, and then finally the hydrogen atom.
Professor,
Yes?
what was the y again?
The y is this factor right in here.
Okay.
Just the one minus 1 okay, sorry.
Wait, would the y include the negative? Or does the y include negative, or just 1/2 kx squared?
Oh, it can be negative.
Wait, y is e minus 1/2 kx squared? Y is e minus 1/2 kx squared?
No, just a minus 1 x squared.
Okay.
All right.
So, Mr. Dorio, when you said this hydrogen atom, does that include the hydrogenic atoms?
Yes, any single electron atom. It's just, since you brought it up, of course, now you have to be a little careful about the charge on the nucleus. So you have to put down Ze as the charge on the nucleus. So the force is going to be, of course, 1 over 4 pi epsilon naught Ce squared over r. All right, what fun. Now we're going to change gears. Oh, really? What? We're going to start to talk about how, as we were becoming aware of this, and we're really talking the 1920s, that's when Schrodinger was about 1925. So by the late 1920s and into the 1930s, we began to wonder, how does all of this affect the atomic nucleus? The atomic nucleus, we were only aware of it for the last 20 years. For the previous 20 years, we were aware that a nucleus existed. Do you happen to remember who discovered the atomic nucleus? Rutherford. Rutherford in 1911 discovered the nuclear atom. So people were beginning to wonder about the nucleus. At first we were just treating it as almost a point mass and a point charge. But then we started to ask, well, what's really going on in there? And so they started to apply Schrodinger's equations to what was going on in the nucleus. And we're going to talk a little bit about that now. Most of the work was done primarily by the great Italian physicist Enrico Fermi in Rome in the 1930s. And what we'd like to do is talk a little bit about the atomic nucleus, and in particular, how do we learn things about the atomic nucleus. The first thing is, we weren't really aware of nuclear activities because nuclear transitions are much more energetic than electronic transitions. When the electron is transitioning from one energy level to the next, it usually involves a few electron volts. As you remember from our experiments on the Bohr model of the hydrogen atom, nuclear transitions, when an atomic nucleus goes from one energy state to the next, it typically involves a few MeV. And so immediately you say to yourself, gee whiz, the electronic transitions give me visible light and it's a few electron volts. Nuclear transitions are a few million times more energetic. So of course I'm not going to see any kind of radiation coming from the nucleus. If you have millions of electron volts, you're expecting fantastically short wavelengths. High energy means high frequency and short wavelengths. So that's one of the reasons why we were sort of unaware of nuclear transitions at first, is because they involve huge energies, not small energies. Now, just like we were doing with the studying the electron, when we were looking at the hydrogen atom, of course, you had to put the tube in the power supply, and I like to say you were just giving it a little kick. You'd kick it with some energy. And to get the electron to jump from a lower energy level to a higher energy level, you kick it with a few electron volts, and up it goes. How do you get in there and reaching a kick the nucleus? You want to give the nucleus a kick with enough energy to raise the energy level of the nucleus. It says, how do we reach in and give the nucleus a kick as we did with electrons? Big question mark. Well, to do that, of course, you're going to have to reach in there with a lot higher energies. And I'd like to talk to you a little bit about how those higher energies actually work. Let's see here. To do that, I'm going to use some notation, and I'd like to introduce the notation at this point so that we can go back and use the ideas and talk a little bit more specifically about individual atomic nuclei, and then we're going to reach in there and really explore. And I'm interested in two things, of course, the results, but how the experiments are actually done. First off, we're going to change things a little bit. I know many of you are used to the periodic table and how things work with the periodic table, but the periodic table is designed specifically to make it easy to use by chemists, not by physicists. And we're going to change the notation a little bit. For example, I'm going to use notation like this. X represents the chemical symbol. And then there's going to be a pre-subscript. I'm going to write it down as A right now, and a pre-subscript. So we've got a pre-super and a pre-subscript. The superscript is A, the subscript is Z. What we're talking about here, folks, let me give you an example. I think we used chlorine, yeah. So chlorine, its element number 17. Its mass number is 35. I want to explain a couple of things and then why it's useful, and then we're going to look at the physicist version of the periodic table. First off, the subscript is the charge number. So write it down like this. Let me use a different color because I really want to emphasize this. We'll use red because that's really important. This subscript is number of plus charges. That's the number of plus charges. Most of the time, number protons. But I'm going to put that in parentheses because obviously if I say most of the time it's the number of protons, not always, not always. And the superscript is going to be number of mass particles. Number of mass particles. Most of the time, number protons plus number of neutrons. In parentheses, because not always. Oh, and by the way, the chemical symbol implies the number of plus charges. The number of plus charges implies the chemical symbol, right? Hence, therefore, these two numbers are redundant. And not only do physicists hate to be redundant, we don't like to repeat ourselves. That's a given. So most of the time, actually, we actually leave that off.
Have we encountered a case where the number of protons and the charge is different in this class yet?
It's different than,
In this class, have we encountered a situation?
we very well may, yes. But it's not, it's typically not, it's obviously not a chemical element. It's other particles that have numbers other than numbers of protons. So typically we leave the subscript off because I know by now, physics 6, you guys all have the entire periodic table memorized, right? Okay, yes. You're rolling your eyes as you say that. No, I do not expect you to have the entire periodic table memorized. However, the information is always available. If I did something like this, if I was to ask you this question, if I was to say, U-238, how many neutrons? All you have to do is to figure out what the subscript, the missing subscript is. But it's uranium, so it's easy to figure it out. Or maybe some of you know. There's a periodic table. Is it the last page of our book or so? Check it out, check it out. I think there's a periodic table at the end of our book. All you have to do is find uranium, make sure. Somebody said it correctly, but I'd like you to look it up. Is it on the inside cover?
Here it is.
I don't know what is the number 92.
That is correct. You notice it's element number 92? So all you have to do is look up the 92. Most of the time I write the subscript in a different color because we don't normally write it. So it's 92. So you know now what we have is 238 nucleons, 238 nucleons, which is a word that means protons and neutrons. 238 nucleons minus 92 of them are protons, so what do you get? 146 neutrons. So what I'm saying here is very often you'll need to know the number of neutrons, and all you'll have is the chemical symbol and, listen to the new word now, the isotope number. So the chemical symbol uranium, the isotope number is 238. And that means you're dealing with a specific nucleus that has 238 nucleons, 93 protons, 146 neutrons. And of course, you'll always be able to look up the missing subscript because your book will be handy. That implies something else. On the periodic table, when they give you the mass of an element, they give you the average mass. Because in chemistry, you're usually dealing with a sample of something. What's the average mass of uranium? It's not 238. It's 238 point something. And that's because there are different isotopes of uranium. In physics, we deal with the individual nuclei. That's why when we create a periodic table, here it is. This is the periodic table as far as a physicist is concerned. you go to uranium, which is right here, and you'll notice a whole string of boxes. All of them are uraniums, and they have different isotope numbers. So in uranium, we have 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 different versions of uranium up there. So remember that when we're dealing with any element, we're dealing with a specific isotope or one particular number of neutrons. And they all behave differently. So it's not like all uranium is the same. To a chemist, all uranium is the same. It has the same chemical properties. Why the orbital electrons are the same. But to a physicist, they're radically different animals. So we have a ton of different objects on the periodic table. Now let's talk a little bit about that chart because it was really interesting to notice, and I think that chart is exactly the opposite of what I put on here. So let me see. Yeah, it is. So let me modify my notes here. It's pretty interesting that if you take samples and plot down here, I'm going to put N, the number of neutrons, and Z, the number of charged particles. And on this chart, draw a straight line where N equals Z. You discover that the elements that exist on a line which starts out as N equals Z, but then goes above. And then comes to an abrupt stop someplace. Implying that for some reason you need to have an equal number of neutrons or slightly more neutrons than the number of protons to have an element work. Now, can anybody guess why? Or what might cause this? You don't even have to tell me why, but what might cause this result? Why do you have to have neutrons mixed in there?
To keep us, the protons kind of separated.
That's correct. It turns out the nuclear force, the force that holds the nucleus together, is a force utterly different than other forces that we're aware of. For example, gravity or electricity and magnetism, both infinitely ranged forces. The nuclear force is a very short-ranged force, by the way, about 10 to the minus 15 meters. That's all the further the nuclear force will reach, 10 to the minus 15 meters.
That's the strong force?
That's the strong nuclear force, and it can be saturated. If you try to get too many protons too close together, the repulsion, the electrical repulsion, is strong enough to blow the nucleus apart. And so you start packing, one way of thinking of it is pack neutrons in to spread them out a little bit. Neutrons actually add more nuclear force and dilute the repulsive Coulomb force. So at first you can have an equal number of neutrons as protons, but then as things move along, the number of neutrons have to get larger and larger to spread things out enough to add enough nuclear force and spread things out enough to keep things from flying apart. It's kind of interesting, and let me just show you a quick implication here. It's kind of interesting to notice that when you begin to plot particles in the nuclear force, the nuclear force is kind of a nuclear well, which is like this. Not exactly squared off on the edges. And like you might expect just from our work on the hydrogen atom, there are energy levels in the nucleus like this. And I'm going to split this thing in half because this is the number of neutrons and this is the number of protons. And at any given level, you're allowed to have two particles. So there's two protons here and here. I'm going to show, what am I going to show? Boron and carbon. So let me show carbon-12 to begin with. Carbon-12 has 6 protons and 6 neutrons. This is carbon-12. Carbon-12. Like that. And everything looks real nice. There is, however, boron-12. And what element is boron? It's not element number 6, it's what? You see it there?
1 second. Five.
Aha! It's element number 5. So immediately you know what I'm going to do differently, don't you? For boron-12, we're going to have a few energy levels. We're going to split it in half like that. But it's boron-12, not carbon-12. Well, there's going to be 12 nucleons, right? Except this time 5 of them are going to be protons and 7 of them are going to be neutrons. So look. 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7. Ooh, notice. We have a neutron at a higher energy level than the hole where a proton would fit. So immediately we are suspicious that this is unstable and it will want to do this. Convert a neutron into a proton. So even though they're both 12 nucleons, carbon-12 is very happy, it's very satisfied, it's very nice with equal numbers of protons and neutrons. But in this case where you get too many neutrons and not enough protons, then there's a proton hole, so to speak, below the energy of the neutron, of the final neutron we put on them. So it's going to want to decay. So imagine, how do you think it's going to get, how does a neutron decay into a proton? I think you got it right. You may think of a neutron, and don't push this analogy too far, but in this case, you can think of a neutron as a proton plus an electron. It's not made of a proton plus an electron. I think what we're going to discover is that it's made of the pieces of a proton and the pieces of an electron. An electron is not allowed to exist in the nucleus, so it cannot be made of an electron, but the pieces of an electron. Well, it doesn't matter for our analogy right now. What we think of as the neutron decays to a proton plus a beta minus. That is an electron. It's called beta decay, so I'm going to use the beta symbol there. By the way, some books, I don't remember what our author does, some books do this. Proton plus an E plus. Plus an E minus. That is, so this charge plus that charge equals a neutral charge, and some textbooks call it a beta decay, some call it electron decay. It just depends. We thought these were two different things at first, that's why we gave them two different names, it doesn't matter. Beta minus is an electron decay, typically out of a proton, converting it from a neutron into a proton.
Is that why neutrons slightly more massive than a proton?
That's why a neutron is slightly more massive than a proton, yes. Because, by the way, not only does it contain the mass from which you build an electron, but it's also the energy involved. Remember, E equals mc squared, don't forget that. All right, well, these are kind of interesting things, but how do we learn about this? This is going to be one of the interesting topics right now, is how do we learn about this kind of thing? And I'd like to talk with you about how nuclear research takes place. Really very interesting, because 1930 was a big year. Back in the first part of the 20th century, lots of things were happening. In 1930, a very interesting set of things were going on. One totally unrelated, or at least it seems unrelated. This is the year that Hubble and Humason first noticed the hint of the Big Bang. This is the year when Enrico Fermi started working on these kinds of research projects. This is the year of E.O. Lawrence. I'd like to talk with you a little bit about him. and what he did. He built the world's first particle accelerator. Very exciting. I was lucky enough to have a professor who was a student at Berkeley that year, 1930. And Berkeley, back then, Cal Berkeley, decided that they wanted to have the world's finest physics department. The only way to do that is to have the world's finest physicists. That's where it comes from. And so they searched around the world, hired all kinds of brilliant people. One of them is J. Robert Oppenheimer. I think you might know that name. Who was he? Yeah, he was the guy who managed the scientific side of the Manhattan Project. And another one was Lawrence. They hired Lawrence in 1930. And my understanding is all the students were really excited. Here you're getting one of the world's top experimental physicists coming to Berkeley. So we're going to be able to take classes from this guy. Wonderful. They never saw him. He was hired, he came, he showed up, he went into his lab, you didn't see him for 6 months. For 6 months he was just in his lab, nobody saw him. They knew he was there because his name was on the door, but that's all they saw. And he was working away. What was he doing? 6 months later, he came out of his lab holding in his hands the world's first particle accelerator. It's called a cyclotron. That's how big it is. In fact, there's a picture in your book. I saw it in your book, and I wrote the page down. To find a picture of Lawrence, oh dear. Lawrence, 1930, cyclotron, and I didn't write the page down. There's a picture of him holding the cyclotron in your book. Maybe you can check your index, because I'd like you to see this happy dude with his cyclotron in his hand. Look up cyclotron or look up Lawrence E.O. Did you go to the index, or are you just randomly flipping around trying to find the picture? There's a lot of pages if you're just going to randomly flip.
It's 926.
11:35. Okay.
Page
926?
Yeah.
Say it again.
926?
926. Yep, that's the picture. There's Lawrence, and he's holding the cyclotron in his hand. Yep. Page 926, there's Lawrence himself with the cyclotron in his hand. Okay, I'll tell you this part, and then we'll go to talking about how the cyclotron actually works. Lawrence has now the world's first particle accelerator. He's happy with it, and what it does is produce a beam of charged particles at high energy. Aha, we're finally able to reach into atomic nucleus and give it a little kick and see what happens. That's what the particle accelerator is all about. It's a way by which you can excite atomic nuclei, just like we were exciting hydrogen atoms in the original experiment that we did a few weeks ago. Now we can reach in and give a little kick to nuclei with this particle accelerator. Everybody was delighted. Everybody knew this was extremely important. That's why this invention won for Lawrence a $500 prize. In 1930, that was a pretty good piece of change. He said, thank you, he took the money, he went right back into his lab, he used that money to build a cyclotron twice as big. Why? That means more energy. More energy means you can reach deeper into the nucleus. Cyclotrons and particle accelerators have been getting bigger ever since.
You got $1,000 for that one?
$1,000 for that one? I don't remember. I don't ever remember hearing about the second cyclotron. However, just to demonstrate to you, and I'm sure you're aware of this, but just to demonstrate to you, these things have been getting pretty darn big. They started in 1930. The first one was this big. Now there are two big machines on Earth that have been functioning for a few years. One is called Fermilab. The other one used to be called CERN. They now call it the Large Hadron Collider. Do you know how big those things are? Their circumference is about 3 miles. Okay, from that big to 3 miles, these things have gotten to be monstrously large. And nuclear research has been going on ever since. Using things like cyclotrons, you can build heavy nuclei. Let me borrow a textbook here, if I may. Back to your periodic table. Uranium is about the heaviest naturally occurring element. You see number 92? And then right after that, there's 10 more elements. They are synthetic, built in a cyclotron. Let's just name them, see if I can without reading the name on the bottom. I can't even see the name on the bottom. Neptunium, plutonium, americium, berkelium, californium. Does anybody want to guess exactly where? Einsteinium, fermium, mendeleevium, and nobelium. Then element 103 is lawrencium, named after E.O. Lawrence. By the way, those 10 elements, from neptunium to lawrencium, were built very quickly, one after the other, in the cyclotron at Berkeley in the 1950s. And I just want to mention his name. It was virtually all done by one man named Glenn Seaborg, a brilliant physicist who figured out how to build heavy elements which don't last very long. Those elements always, the nuclear force is totally saturated and the elements decay radioactively. So there's no practical reason to build those heavy elements, but there certainly is an excellent scientific reason to test Schrödinger's equation. Schrödinger's equation predicts what these elements should be like. We can build them and study them before they fall apart radioactively, and they behave according to Schrödinger's equation. Not only was, I got to tell you this too, not only was Glenn Seaborg a brilliant physicist, but he was also the craziest Cub Scout leader in the world. We loved the guy. He was one. You might notice element 106 is Seaborgium. They don't name things after you until you die. He passed away a few years ago. He will be badly missed. So, the periodic table expanded dramatically because of these things. There's no practical reason to build these heavier elements except to test our theories, to test our ideas on nuclear physics. Now let's talk a little bit about how a cyclotron works and what we do with the results from a cyclotron. If you take a cyclotron, like let's use this first little one, okay, because it's easier. It's symmetric top and bottom. Take the top off and look down on the, and you see what almost looks like a perfect circle like that, except the center is missing. They say it's manufactured by two Ds, the double D like this. And what they'll do is inject particles, protons, right in here. So here are the protons being injected right in the center. And while they do that, this plate is heavily positively charged. This plate is heavily negatively charged. Oops. This plate is positively negative, positive down here, negative up there. So of course the proton is accelerated heavily towards that plate, gaining some kinetic energy. Now simultaneously produce a magnetic field at right angles to the electric field. So the electric field is functioning in this direction, the magnetic field is functioning in that direction. The magnetic field at right angles to the velocity of the charged particle provides centripetal force. So the particle accelerates towards the upper D and immediately begins to do uniform circular motion like this. But of course you know that while we're in this region here, the electric field, which is concentrated in this area, has no effect on the particle. So while the particle is there, change the charge. This one now becomes negatively charged. This one becomes positively charged. And the particle is once again accelerated when it gets into this region here. It's accelerated across there. It now has an even higher velocity, but it's still in the same magnetic field, so it has the same tendency towards uniform circular motion, only this time of higher radius. And as it's swinging around there, you change the charge again. This is negative, this is positive. We're accelerated again, and you get the idea. You just oscillate the charge back and forth on these two Ds, and that way, every time the particle is in this region and the charge is changing on the plates, it's coasting in uniform circular motion. As it goes through this area, it's accelerated back into uniform circular motion, and it spirals round and round until finally it reaches the physical limit of the device, and out comes a stream of charged particles at extremely high energies. Those particles are then fired at a stationary target, typically a very thin foil, so that the protons, the high energy protons, will most likely strike one nucleus or nothing. One nucleus or nothing. So yeah, there's a pretty good stream of undisturbed protons coming right straight through the chamber like that. But some of those protons do hit nuclei and essentially break them apart. So out comes all kinds of scattering materials out of here like this. All we have to do then is to put up detectors to try to figure out what kinds of particles are scattering and measure the angle. If there is a Compton-like event, if there is a photo-like event, get the angle. Get the angle and the particle that comes out, and the energy of the particle that comes out. From that data, you can begin to understand how a nucleus is built. Way back then, a physicist said, it's a little bit like taking two elegant Swiss watches and banging them together, and then trying to figure out how to build a watch by looking at the springs and the cogwheels that come flying out. Not a very elegant technique, but it was the only thing that worked. So that's the core of nuclear research. You accelerate particles, you slam them into stationary targets, and then look at the junk that comes flying out. Measure the charge, the mass, the angle, the energy of the outcoming particles, and from that you try to figure out how the nucleus is formed. Of course, the bigger the cyclotron, the more energetic the particle, the deeper into the nucleus you are probing. That's why we build these things bigger. Bigger is better. And they've got to be monstrously large, as I said before. So it's a very interesting form of research. That's how you do it. Probably, you know, one of the most challenging parts of all is to make that target. Can you imagine, typically this target, most commonly I see this target made of gold, because gold is so easy to deal with. That target is 100 atoms thick. That's how thick you make that target. That's not easy to do. How do you make something 100 atoms thick? It's not easy to do. Typical gold foil is gold foil target is